There are like different protocols, but the first implementation that solved the double spend problem in the sense of make an incentive way for doing that. It's the meaning of the people that are calling the cyberpunkers. That cyberpunkers are researchers, are people out there in the internet that make a special hoof for looking a new world, a new world currency that don't want to have authority, um, that don't have anything with the governments and so forth. But this kind of cyberpunker dream that it's an interesting way to see the economics out there. I started thinking in very different approach out there to solve this world currency. But let's see in this video and this webinar is all about the Ethereum 2.0, and we can saw here that the Ethereum 2.0 have different papers out there that we saw in another videos, and the more incredible implementation about this kind of protocol, it's this paper that is called the Casper, the friendly finality gadget, that it's calling Casper FFG, that is all about the algorithm to reach the consensus and how to reach the consensus in the safety way that it's a property that BFG protocols have, and also how to reach the consensus in the partial connect asynchronous network. This partial connect asynchronous network is a thing that the BFT protocol implementation is dealing, and this is why are so hard to build a BFT protocol in a synchronous network approach. And this is because researchers like Fisher, Lynch, and Patterson showed that there is no deterministic protocol for the BFT problem in a phase of a single failure. So this impossibility that it's called the impossibility of Fisher was a big deal for the BFT protocol implementation, because in a synchronous network you are dealing with a complex data, and this complex data is in a communication topology of the network, and this topology communication is based in that you are dealing with a big delays in how this message is passed and spread across the network. But let's see more things about under the hood how this protocol specification works. So you can find in Google all the things that I am doing right now. You can check for yourself. So you can go to the Ethereum research, and there is two kinds of hooks. The research, that it's a page that is working like a block, and also you have the Ethereum research hub. So anyone can log in here and make a proposal for the protocol specification, or any kind of thing can help the blockchain ecosystem. So you can find here that it's a block, and you can log in for yourself, and you can make a proposal that makes sense in math, that makes sense in computer science approaches. So let's move to see this Ethereum research GitHub that is more interesting because it's the code, it's the math, and the papers. So far in this webinar we're talking about the Beacon chain. In another videos we saw different kind of protocol specification, and we are talking about right now the beacon state. And where is this beacon state? Okay, I have this interesting Python simulation that shows how this beacon state work in the real world. Remember that this implementation is still in experimental way, so there is a lot of things to figure it out in this kind of protocol. So let's see this Python simulation. So refresh the page, and you can see here right now the beacon state start. In this beacon state you have a genesis time, you have a genesis state, and the block 0 that could be a 1 0. Then this beacon chain that is the blue in the center start to growing across the time, and all the aquamarine positioned in a circle with the beacon chain in the center are called the shard chains that are a complementary chains for this beacon state for handle more data and handle more transactions in a safety way. Sharding is an approach for dealing with the scalability trilemma, and this scalability trilemma also is called the blockchain trilemma. And this part of the trilemma is the scalability that it's based on transactions per second. Then also you have the security, and you also have the decentralization. The meaning of decentralization is for the setup that also it's called the permissionless setting, but also have other kind of meaning out there. But in this sense, in this video, we are talking about decentralization for the permissionless setting. And what is this permissionless setting? This permissionless setting is about that anyone in the network can join with don't have permission for a central authority. So anyone with internet or anyone that have a connection with this network can join if don't have to make a permission for this. And this is the meaning of decentralization in the scalability trilemma that is also called in the scalability challenge. And it's a bottleneck in the blockchain approach and so far in the BFT protocol implementation. So you can find here this beacon state start to run out with all the shard chains out there, and the things that you can see here that are like arrows are the crosslinks. That crosslinks are calling also a number of attestation, and this attestation is connect the shard chains for the beacon state and make the validation think for start thinking in the longest chain, and this longest chain is the meaning to validate all the blockchain approach. So let's move to the code and see interesting thing about this beacon state. So let's open a new window. If you have any question, you can ask me anything in the comment section. We are live, so let's just see this implementation in the Trinity code. We have here the Trinity code that is the code that the Ethereum Foundation published in their official GitHub repo. So let's move to see interesting things here. This webinar is all about the beacon state. So let's move to see more things about this beacon. So you can find here different folders. So In these different folders you have different things about this implementation, and the heart of this implementation is the consensus. So let's find this consensus, but in the beacon state, because this consensus works in the different ways that the protocol needs to reach the consensus. And the hard part of this consensus is dealing with the partial connect asynchronous network. And the mitigation plan is the sharding, meaning that sharding is so experimental in blockchains. The first implementation of sharding in an industrial way was the Silica blockchain that have approach in the sharding meaning. And this sharding meaning it's about to start to build shard chains with shard blocks. And these shard blocks have only one part of all this data. So in the side of the client don't need to download all these beacon state. So it's a way to make a stateless client and a stateless node. But in an optimistic way, it's very difficult to reach the consensus in the partial connect asynchronous network. So in the scope of this kind of protocol, you can find other different papers that explain these things. So, but let's move more interesting things in this the beacon state. So you can find here this beacon state. In another video we saw this beacon state. It's a very complex thing. And let's move to the fourth choice. We saw in another videos that this fourth choice is an implementation of the paper of Sobolovsky that we can saw in the official page of Ethereum. So let's move to see this fourth choice. That is a big one implementation in the BFT protocol that the Ethereum Foundation proposed. So let's move to the folder of papers there is, and you can find here the Casper TIFFG. Let's see this paper to understand under the hood how it's about, or what is all about in this uh, fourth choice rule. Let's download to have a better. So this fourth choice rule, as I am speak, is a adaptation of a paper of Sobolovsky that it's calling this algorithm the greedy habits observed sub 3, that it's calling Ghost for greedy habits observed sub 3, and it's algorithm that the finality of this algorithm it's a way to connect all the blocks that you have, but you need to find one property that is so difficult to fake, that is so difficult for an attacker out there that could try to, I don't know, make a different kind of attack. So this algorithm prevent that kind of attack for civil attacks. I don't know, there is a lot of attacks out there. But it's prevent the way for the thing of the adversaries. So let's move to see this adaptation of this algorithm, and you can find all the math here and all the definitions. But let's see the original paper to understand the foundation of this fourth choice rule. That work because it's a very interesting way to understand this kind of application. If you want to build a BFT protocol, because this BFT protocol can you build a social network You can build a social network, you can build any kind of decentralized application, but also you can build your own cryptocurrency, maybe other things that don't exist yet. But I think the VFT protocol is a big deal in the meaning of understand the neutrality of the network, the neutrality of the internet out there. So let's see this original paper. So let's find this original paper to understand the algorithm. So let's copy this. It's in the reference one, so we have, and it's a EPRIM. And it's a large paper that have different things. And you can deep dive in this very good paper that have interesting ways for see how to reach the consensus. But the only part that we are seeing right now is the algorithm to find how this adaptation works in the beacon state. So this virtual rule is a way to prevent any kind of adversary out there. So let's move to the algorithm. The algorithm is in a fig here. Oh my. So we can find here all the things, all the definitions. You can find here the way that attacker is trying to make things that the consensus is not healthy for the consensus in codes. So it's attacker secret chain. So these virtual rules prevent this kind of attack. And remember that it's interesting this virtual rule because you have a lot of chains here. You can see that you have, in some sense, one beacon state for 6 or 7 search chains that are connect between cross links that are number of the stations, and this number of the station is to be random, and you start to thinking in the beacon randomness thing that is the specification of rundown, that is the specification of BDF, that it's a delay function that have an input an output that it's so random that you can prevent this any kind of attack. So you are dealing with a complex connection here. So let's see this gravity heavy observers of 3 to understand the things in the code and also understand the algorithms thing. So you can find here the FIS algorithm that is called the Gravis Holvet Observer sub 3, and it's a algorithm that have an input in the block 3t. It's only the meaning of the input, and you have 4 phases that this algorithm needs to do. So in a set of B gets this genesis block. So you can start thinking in this way, refresh this to see this genesis state. This is the genesis state. So in these 4 rules, this start to get this genesis block. Then if a children of this kind of input, calling the B, is equals to something that could be a nil, that could be a null, that could be a zero in some sense, but in code you can imagine that could be a nil, that could be a null, that could be something that it's not about the genesis block. Then return the B, the thing that you want, and exit. And the meaning of technical way to make this exit are calling voluntary exits. That it's interesting code that you can find in the beacon state. Then in the 3 part, else update P, and this is the interesting implementation that the Hivis observed sub 3. have to get this max of the subtree tree with the condition that have these children. So you start to thinking that this implementation exit when you have the thing that you want, the thing that the algorithm needs, but update B in the way to make a recursive. So it's a way to handle this kind of algorithm. So in other words, you need to start thinking in a specific function. I think that the chain that you're trying to build in have specific things to connect this algorithm. And in the Casper specification, we can find that they calling this the height function. And let's see what it's all about, this height function, to understand the adaptation of this protocol. So let's see this paper, and they make this height function to understand the adaptation of the ghost algorithm. So in this fig, we can see that the sport rule start to make more sense in how to decide what is the correct chain, or what is the way to connect this chain in the meaning of the protocol specification. So far the wave function, remember that blocks are packaged of a kind of data. So in this block you can find different data. In the proof of work chain that is calling now the Ethereum 1 2.0, you have a block. In this block you have a web function, you have a web, you have timestamp, you have data, you have the data of the parent of this block, you have different ways to see handle this data. So the only thing that make to connect different chains in this way is make this adaptation in the ghost that that the that the implementation calling the for each rule to make to connect this data in different ways. So this is the only function that will work. And then find that in this representation that they make, that the way this wave function in the sense, it's the thing that this beacon state or this Genesis state needs to connect the other chains in a safety way. So let's see how this adaptation works in the real world scenario. So you have here the full choice, and you have different things that also call in the LMD ghost, a higher slot, and the scoring, that it's a kind of membership to make a double protection or make a double successful algorithm. This kind of protocol that is called in the Casper basics uh, have also other paper to understand that is calling the unity of this kind of two papers. Let's see this paper that find the mathematical clean in codes to see if this will work for the the consensus state of it's a failed implementation. So on this protocol, I start make this evaluation of in a math sense for all the things that have, and the main ingredients is the Casper FGG and also the LMD Ghost for choice rule. So let's see things about these things, and we have here the adaptation of the protocol of the ghost with the main two ingredients: the Casper FGG, that is the algorithm that maybe in some ways is the height function, plus this for-short rule adaptation. And you can find that it's very similar in the way that in the way of the first algorithm, that is this adaptation. The first method is equal, then change in the second when this state be most recent attestation of the n validators. So the adaptation is that you, in this kind of protocol, you have attestation, and this attestation are the things that connect the beacon state with the shard state. So it's a way to handle this cross-link thing for make a complementary consensus state, because you are getting data for one proof of work chain. So this is the finality of this gadget in some sense. Then you have that this big has children, and you have here that make the same thing. They are get masked, but with a different kind of input. Then return the thing that you want. So let's see this in code. Let's see this adaptation. And let's start to thinking in this. So def let's see this transaction, and I start to make this. So you have the score block, find the root. So this object have a root, and you have the in. Then return the in from bytes the root by order is equals to big. Then this make start to think in this for sure rule. So this LMD goes score have a base score. So the score is a tuple of the weight and the int. Then you start the decorates meaning. So you have this first object that start to make sense in the way that the beacon state make this for sure rule for handle the safety condition that the consensus needs. So this decorator start this way, and this self score have the same input, and you can find here that it's when this get the genesis state. So you have the int, so this object could be handle the things for the score. Then you have another decorator here, could be the decorator of this object, that could be the same kind of input, or in this way you have the LND score. But this is will be an object with a sense that it's a boolean. So return the self and score so you can find here that this star makes sense, but the score is a thing that maybe in the algorithm could not work so properly. You need to make the real world scenario, that is the code. But let's see. Okay, you can find here that this also for sure rule have hybrids that could be a variance of this kind of protocol specification. So it's an interesting way to see that this hybrid starts thinking in the highest attestation epoch, and this is the way for make a score. So if you have a score of the attestation, you start to thinking in how to handle this. So this variant of the for sure rule is getting this membership thing for get the highest attestation, and this is double protection for the protocol specification. So let's make our corrector. So you have here that is a self order. Okay, order that could be any. So this is will be a boolean because you need to decide is or not is. So if a conditional statement, so it's instance of other LND. So you need to make a good code. So this could not be boogie. So return not implemented. Then return self score other score. Then we can make here how to serialize this. So let's serialize the self thing. Could be an objects of bytes. The protocol specification start with the CCC approach. So I need to return the serialize thing. So it could be another score. Def. So return serialize. Maybe this is gonna be. You need to start thinking in how to serialize this for a better handle. So the score this way. We have the serialize thing, but it's a vector of the same thing. So this hybrid of the future rule needs also the most recent measures. So these most recent measures, it's a way to difficult to understand the protocol specification. So let's make a class method. So the serialize. We also have its CLSD data. So you need the bytes here. Empty toss score. So this score is serialized in the way of CCCD. So you need to put the data of this, then you set this is equals to the serialized vector CCC would be something have the same meaning. So far. So you need to start to deserialize this. If you serialize this, then maybe we can start to thinking in the way to get this data in the genesis, because remember that the genesis it's a unique state. So this genesis have the genesis state that is the beacon state, because it's the chain and coordinate the things. So the genesis block, that is a base beacon block. Start to think in this base score. And remember that the score are in a tuple. So you have the score, this. So the minimal unit in the Ethereum protocol is the way. So you need to start think in the units. So the score log by root, it's a 0 root. Then you need to return the CLC score. Then you can start thinking in the variance of this. This variance is justify part with the highest attestation epoch in this condition. Then you have the most recent measures. So in this hybrid you have the most recent attestation of any validators. In the other way you have the justified part for the highest attestation. So in the two ways are a variant of this algorithm. So far you need to start thinking in the scoring thing. So make a membership of this, so you can make a indistinguishable thing with the lowest attestation with the highest attestation. So far you can compute slots since epoch start. So the slot, have this slots per epoch. So return the slot in a condition. We have the slot. So I need to compute start slot and epoch. So So compute the same way. Slots. So this is slot per epoch. Some condition of the slots. So you see the epoch have these epoch boundary blocks and pairs. So suppose that you have this for a chains and a slot, and this kind of a slot make different things for observable blocks. First approach. So the way that the epoch are connect, or the boundary of this terminate a chain define ABV, the epoch boundary block of V to be a block with the highest slot less than or equal to every epoch. This is the principal condition. Highest slot less than or equal to GC for every epoch. So you can find here that compute the slots since the epoch start. So you need to compute the slots in that way. So far, it's a way to make this approach in a safety way. So let's zoom here to see more things. Okay, so far we make this membership score. We understand that the LMD goals have a variance of this kind of protocol. So you need to start thinking more about the context of this, genesis, effective balance, same way of the slot per epoch. You need to think in how to deserialize this, how to get this checkpoint, because it's all about to get this checkpoint in the height function way. You also need justify the checkpoint. So you can see it's a complex state of this. Start thinking in the attestation. And then can make this like this in the way of the class LMD process score surface for choice scoring. You have to init this. It's a self. So far you need to make store known self score to store class method constructor for get score class so type this score, then need to return this score. So the score self block base become block, and then need to connect with the base score. Return self store with the config scoring block. So far we saw how this class, that is the membership of this LMDA goes, have a tuple in the way and the int, and this int is how to serialize and how to get this from the genesis. And then we have in the finality of this object the LMD goes score for rule scoring. That it's all about to have this type of a scoring. Then you need to return this score and then return the scoring block. So make a good connection in this height function way. So you also can start thinking in the scoring, how to work. So you have the scoring, that is a self. You have the block, have the base, become block. So have the LMD score. And this is the way for the root. Block meshes hash tree the station score self get lattice distinct balance, because you need to find the highest there will be another T, but let's see the block root score. Also is a score. That's the variant of this kind of protocol implementation. And you have the block by root is equals to the root. Then you need to start in the way of the protocol to return the things that the protocol specification needs. So far, you need to make return the score with the attestation score with the root score, and that's all. Okay, so far we see that this variant of the function rules have this membership thing, because you are dealing with the highest attestation and also the lowest attestation. You also, in a variant of these, are handled with the most recent attestation. So it's a way to handle these two kinds of future rules. So about the finality of this hybrid and this adaptation of the paper of Sobolowski is that you make a properly idea that we use the heights of the subtree created by the fork and find a heuristic way to make this. So it's a heuristic thing that we can see in the paper of the Caspic, that this condition is not properly working like that. The chain is not working, and the reach is not dealing with the partial connect asynchronous network. So this justified chain, it's this way. So the scoring of the things are interesting, how this is connect. So let's see more things. So this could be the boogie thing of this. But let's see this virtual rule in the first script for understand this. So you can find Ethereum research. And let's find this. So far in the Beacon chain implementation, but let's see this virtual rule. So you have here the host. So the primitive, you have this condition that are only 100 lines of code. So you have get the height, that it starts this gate function of the block, return the block to handle this cache, then get the ancestor. This is all about the wave function to start to make sense for return the block as you want. Then the game is at this block, then this parent needs in some way works like any kind of a block of there. The interesting approach here is the attestation that needs this validator index. So far we start to look here where is get claim winner. So who will win this game of attestation? So you need to make this boogie representation. So far in the LMD goes, you start thinking in the scoring that this is attestation score is a self-get attestation balance. So it's a very way to make in this attestation balance. That's in the way of the total of the height function. So also you have just the child. You have this for child. Power 2. Then you have the ghost that the lattice was in a range of these LED balances. You have also this height function. When these children get the head, when it's equals to 0, return the head. Get per to get head. It's variable. It's funny. And then the simulate chain. It's the way. So in the first script we can see here that it's don't use this variant and don't think a lot in this scoring thing. So this scoring thing is adaptation that make a better code, not a buggy code in the technical way, because you are doing the things that as you want. So far you have here this first implementation of the scoring, meaning of the LMD cost. It's in some way the adaptation of this. So let's see more about this boundary. So you can find that you are dealing with a lot of data here. So for one hand you have the variant. For the other hand you have this membership thing. You also have the bug meaning, but you need to respect this wait function. That is how this justification chain needs for reach the consensus. If this is not work like that, you cannot reach the consensus. Okay. So let's see the higher slot to see more things about this LMD ghost. So in the higher slot score you have also this base score, and it's very a little code here. So let's start for thinking in the class higher slot score, so base score. So you need change the input here for the base for choice rule scoring. Class method here. I'm figuring out how to get the score that you want as the protocol specification. Some way, if you start with the protocol from scratch, you are right now learning how to handle all the things out there for all the data that you are trying to reach a consensus. So that is the hard part. So get the score plus the same input that the LMD ghost works. So because you have the tuple implementation, so return the higher slot score. The decorator of this score works like the LMD ghost. So you are looking for this higher slot for make the things as you want. So this base become block, have the base score, the score is equal to the score block by higher slot. So this block return higher slot score or score. So you can find here that this way is the last implementation in the variant of the protocol specification. So you can find here this part, this is this part, and then return the thing that you want in the pseudocode meaning. So you also make a different variants here, but it's all about the things that you have in the block. So in this block you have the attestations, and the slot it's the way that you can connect the thing that you want. So far, you only have these two conditions. Then the higher attestation, the higher slot, and it's all about scoring and make this membership to reach the consensus in the height function way. So let's see more things about. Let's find here the scoring thing, and it's all about the serialize this scoring thing in the algorithm adaptation of the Casper proof of stake protocol. So the constants that you have here, remember that the principal tuple here is the weight and the unit and the int. So the score in a some way it's equals to the way for the int, and this way have in under the hood have this height function for connect the justificate chain in the way that the algorithm needs, that in this case is calling Casper FFG. So in the scope of this implementation, we find that the scoring meaning have to know to membership the thing. So you have to get from Genesis, then you need to make a score in a tuple of the weight of the unit, then you need to make distinguish difference between the slower attestation and the higher attestation. So if you go to the higher attestation, is because was a successful crosslink in the way that the future rule needs. So far, we saw all about this future rule. So these variants that are the justificator with the highest attestation and POC, and the other variant of the most recent attestation of N validators. Start to make the same way of the height function to connect the blocks in the way that the protocol specification needs for reach the consensus. So so it's interesting this paper because you can find all the math and the way that this consensus or this beacon state needs this scoring for looking this fortune rule. Forget the data that the beacon chain needs for growing the longest chain meaning. So it's an interesting way for dealing with the partial and connect asynchronous. But in the reference out there, there is interesting way for this fortune rule that I could read right now for understand this, because you can understand more the membership thing here. So this safety means that two conflicting chain points cannot be finalized, assuming that there are multi-malicious validators. And the other way, the passive alignment means that supermajority links can always be added to produce new finalized checkpoints. So in this specification, you can find that don't have sufficient details for guarantee its claiming possible without further restriction in the block generation mechanisms. That means that maybe this Casper FGG can reach the deadlocks because deadlocks are the finality for the possible liveness of this BFT protocol specification. So it's hard to see that the possibility of reach the consensus in a mainnet could be a fiasco in the way of this because you are dealing with a lot of chains here. So you also started thinking in if the checkpoints are 100 blocks away for each other and it's expensive slope to generate blocks, then this kind of form may be hard to happen though there is still a possibility. So you can find that this is condition don't work as you want, maybe cannot work properly. So, but let's see in another video that question around. So see you soon.